Welcome to the new lecture in power electronics. We were discussing the diode rectifiers with various loading conditions. Previous few lectures we discussed on R load, the inductive load and the combination of RL load. In this lecture, let us see what happens when the load consists of one resistance and a DC source. So DC source is basically represented with a battery denoted by E. The source that we have is basically a single phase source given by the sinusoidal input, which is Vs equal to Vm sin omega t. As it is half wave rectifier, so we will have only one diode which is connected in the circuit with the help of a switch, so that we have full control over the connection of the circuit and discontinuity of the circuit. The load we have in the form of a resistor, and that is a source of battery denoted by E. The output voltage is V0 and the current which is flowing is I0. The voltage V0 and I0 are basically the average voltage and the average current. So when we plot these on the waveform of the source voltage with respect to omega t, then the source voltage is basically Vm sin omega t, which is sinusoidal in nature, with the maximum magnitude is Vm. Since there is a battery which is connected with the source E, so this is a constant voltage with the source E, considering that the Vm will be greater than E. So we have the Vm voltage which is greater than the source EMF. If we plot the current I0 which is flowing in this circuit with respect to omega t, we will see that the diode will conduct, or the circuit will conduct, at certain angle theta 1, and the current will flow up to a certain point which is pi minus theta 1, and after that there will be discontinuity in the circuit, or the circuit will be turned off. There will be no current. After 2 pi plus theta, the current will again start flowing for the next cycle, and this way the current will flow for I0. So we can say that the diode will be on between the theta 1 and pi minus theta 1, because at the beginning we have the battery which is opposing the source of the EMF. So unless and until this voltage grow to a certain EMF E, the conduction process will not start. So once we close the switch, the diode is reversed biased. So this diode is basically reverse bias and will not conduct until when the source voltage Vs equals the load counter EMF E. So we have the source voltage Vs and there is a counter EMF E. So these two voltages, unless and until it become equal, the diode will not conduct and it will be reverse biased. So it is basically, we can say that when Vm sin theta 1 is equal to the battery voltage, the diode will start conducting, and the turn on angle theta 1 will be given by theta 1 is equal to sine inverse of E by Vm. So this equation is basically coming from here, and here we have the source voltage which is Vm sin omega t. So instead of certain time omega t1, we are substituting here the value of theta 1. So theta 1 is that time period which from where the diode will start conducting and there will be current flowing in the circuit. So theta 1 is equal to sine inverse of E by Vm. The diode conducts from omega to t equal to theta 1 to omega t equal to pi minus theta 1. Hence the total conduction period of the diode is pi minus 2 theta 1. So this is the total conduction period of the diode. During the diode conduction period, we can write the KVL equation in the loop, which is equal to Vm sin omega t is equal to E plus I0 into R. This is the potential drop in the resistor. So we can find from this equation what is the actual current which is flowing in the circuit. So actual current which is flowing in the circuit is Vm sin omega t minus the battery voltage divided by the resistance. If we find the average value of this current I0, we have to integrate from the initial period theta 1 to the final conduction period pi minus theta 1 for the first cycle, you'll get what is I naught, and you can take the time period common, which is 1 by 2 pi, and there is a resistor value R which is already present here. So Vm sin omega t minus E, this we have to integrate over theta 1 to pi minus theta 1, which we will get in this form. Now, if we want to calculate the RMS value of the load current, we know again the RMS value is basically given by the root, and we have the mean, and then we have the integration from 0 to t, and we have the square of the voltage. So here we have the total time period is 2 pi for this t, and the source we have is Vm sin omega t minus E by R. Here we have square, and then we have half. So the conduction period again is theta 1 to pi minus theta 1. So after a series of steps, we'll get in this form the RMS volt value of the load current. Now if we want to compute what is the power delivered to the load, so power delivered to the load is basically the product of voltage into current. This is for the battery, and the I square R term will come because of the resistor. So we need to know what is the RMS current which is flowing in the circuit. If we want to compute the supply power factor, which is equal to power delivered to the load divided by the product of source voltage and the RMS value of the load current, so we can compute using this formula what is the supply power factor. Because the power delivered to the load we have already computed product of E into I naught and I naught square into R. Remember, this is the average current and this is the RMS current. And in the denominator, we have the product of the source voltage and the RMS current. What happened to the diode? So a diode, when omega t is equal to 0, the diode is reversed bias. Hence, we have minus E as the voltage. But at omega t equal to theta 1, the diode voltage will be 0 because here the source voltage will be equal to E. So the period when the diode conducts, there will be no voltage, or it is basically a closed switch on state, diode voltage will be 0. And again at omega t equal to 3 pi by 2, we can say that the source voltage is equal to minus Vm. So diode voltage is given by minus Vm plus E. So this is the entire conduction period of the diode, what happened at the different instants. The peak inverse voltage of the diode will be the total voltage, which is equal to Vm plus E. This is the entire voltage, blocking voltage that the diode has to withstand in the negative half cycle. What happened when the load is a combination of RL now? So we have already seen in the previous lecture only for the resistor. Now let us combine one inductor L. And previous lecture we have also seen that if only inductor was present in the circuit, what would have been happen. So let us see the combination of R and L. What will happen? So in R and L combination, we can say that the current I naught, which is flowing in the network even after the source voltage has become negative. So when the source voltage is negative, we know that the diode will not conduct and it will be reverse biased. But what will happen? The inductor will store some amount of energy which will be driving the network. So the current I naught will still flow when the source voltage has become negative because of the presence of inductor in the load. Inductor voltage we can compute VL is equal to Vs minus VR. So if the total drop in the resistor is VR and the inductor voltage is VL and this is equal to Vs, we can apply the KVL equation here and we can say that the VL is equal to Vs minus VR, where the VR is equal to I naught into R. I naught is the average current which is flowing in the network. So you can see here that after this time period, the voltage will become negative. So this is the negative zone. But if you see from this point to here, there is some amount of current which is already present in the circuit. This would not have present if the inductor is not there. So the output voltage V0 will go negative after a certain instant and then it will come to become 0. So this is the part where the major concentration we have to give when there is inductor present in the network. So inductor present in the network do not make the current to be zero even the source voltage is becoming negative. So I naught flows till the area A representing the energy stored by the L is equal to the area B representing the energy released by the inductor. So there are two areas which are basically overlapping. One area which is the energy which is stored by the L, and the other area which is the energy released by L. These two will be equal, then only the I naught will stop flowing. If we apply the KVL equation in the loop, we can say that Vm sin omega t is equal to the total voltage across the resistor, which is R into I of t, and this is the voltage of the inductor N di by dt. This is due to the forced response because we have the voltage present in the network. When the voltage is removed due to the opening of the switch, then it comes under the category of natural response, and in that case it will be zero on the NHS side of the circuit. So the total solution, if we want to compute the current, will be the sum of the forced response plus the natural response. So forced response is when the source is present, the natural response is when the source is not present. So the solution to the forced response is basically Vm by Z, which is the net magnitude of the current into sin omega t minus theta, where the total impedance of the network is equal to under root of R square plus omega square. And this theta we can compute as tan inverse of XL by R, which is omega L by. The natural response or the current can be computed as A into e to the power minus t by tau, where tau is the time constant and A is a constant. So the total current I of t, which is the summation of the forced current plus the natural current, we can now add, where this constant A we need to compute. So to evaluate the constant A, we can put the time to be 0. So the current I of 0, we can put it in this equation, and here we will get e to the power 0 is equal to 1. So we have A term here, and then we can compute what is A. So A is basically Vm by Z into sin theta. Now this A equation, which we got it from the time to be 0, Vm by Z into sin theta, we can put it in the current expression. Then the total current, we can get it, the expression where the maximum current is equal to Vm by Z, and then we have sin omega t minus theta plus sin theta e to the power minus t by tau, where tau is basically the time constant given by L by R. It is often convenient to write the function in terms of the angle omega t rather than time t. So we can write I of omega t in this form, and wherever the time is there, you can basically substitute the omega t term. So the extinction angle beta means where the total current becomes 0. That can be found out from this expression, putting beta is instead of omega t, and then you can equate that current to be 0. So which reduces in this form. Now remember, these cannot be solved analytically, so there is no closed form solution for beta, and some numerical method has to be applied to obtain what is the value of beta which make this expression to be 0. So if we summarized what we learned here, I of omega t for the conduction period 0 to beta, we get this expression, and from beta to 2 pi there will be no current which is present in the circuit. And the RMS current, if we want to obtain, we can easily obtain from the concept that the conduction period is from 0 to beta, and we can square the current I square omega t d omega t. So these values we can put it in the main current equation square term, and we can find what is the RMS current which is flowing in the network. So the average current, if we want to find what is the average current, so that will be from 0 to beta I omega t, whatever we have here in this expression, that we can compute between 0 to beta divided by 1 by 2 pi. So this lecture we focused on basically the combination of RE and the RL load. And in the previous lecture, we have seen some of the topics combining the resistor and the capacitor with the help of the diodes. So that is all about the rectifiers now. In the coming lecture, we will discuss more on that and then move to the full wave rectifiers and what will happen with the three-phase network. Thank you for now.